Now let's walk through the Verilog code for the multiplier architecture, which we discussed in our previous video. So here is the multiplier module, and we have made it parameterized. So this design can be used, for example, a 2-bit multiplier or a 4-bit multiplier, a 16-bit multiplier, a 32-bit multiplier, and so on. So these are the reset and clock signals. And here we have our multiplicand and multiplier input data, and this is our start signal to the multiplier, and O_result will have the output product value, and O_done will get asserted once the multiplier completes the multiplication calculation and the result is available. So these are the FSM states we have defined, and which are initialization state and load, add, shift, and done state. And these are the internal variable declaration. So R_state variable, which basically represent one of the states, and these are the multiplicand variable and multiplier variable. So if you see here in this design, we have only n-bit multiplicand variable declared, which is register type, and n-bit multiplier variable declared, which is again register type. So whereas in our previous architecture we had to declare 2n-bit width multiplicand variable. And this is the accumulator. Actually, it also includes the carry register bit, which we are going to use. So this is n-bit accumulator plus 1-bit register. So actually it is n plus 1 variable. And this is the count signal, which will basically represent the number of bits in our multiplier. So now let's walk through the code. So on negative edge reset, we are basically resetting our all the internal variables. And once we are out of reset, we will be in initialization state. So in initialization state, we are basically initializing all the variables with 0, and now depending on the start signal, we will be going either to the load state or we will remain in the initialization state. So if our start is high, we will go into the load state, and in the load state basically we will load all the variable values to our registers. So the input variable multiplicand value will be basically getting loaded into the multiplicand register, and the multiplier value will be getting loaded into the multiplier register. Our count will get initialized with the n, and here is nothing but the number of bits in our multiplier, and we will go into the next state, which is add. So in the add state, basically now depending on the value of our multiplier LSB, and depending on the count value, if LSB bit is 1 and count is not equal to 0, we will be basically doing the addition operation, right? So here we are adding our accumulator value with the multiplicand value, and the result will getting back stored into the accumulator. So this R_AC, as I said, it represents both accumulator and carry. So this R_AC is basically n plus 1 bit wide, which will represent both the accumulator value as well as the carry bit value. And then we will go into the shift state. So in the shift state, again depending on the count, if count is 0, then that means we have done our multiplication process and we will go into done state. Otherwise we will decrement the counter by 1 and we will do the right shift operation here. So here you can see that the carry bit plus the accumulator plus the multiplier will get shifted right by 1 bit. And then again we will go into the add state. In add state, again we will check our multiplier LSB bit as well as the count value, and we will do the we will basically repeat the same addition and shifting process. And once we are done, we will go into the done state, and from done state we are basically going back to our initialization state. And now these are the output port assignments. So the register done value will get assigned to the O_done, and once the R_done is asserted, that means our multiplication operation is complete, and now we will assign the accumulator value plus the multiplier value to the output port. So you can see here that from the accumulator we are only using n bits, not the n plus 1th bit, which basically represents the carry. So this is the Verilog HDL code of this particular architecture. Now let's first synthesize this architecture. So for synthesizing, let's select the Yossi synthesis tool, and I will check in the show diagram after running it. So let's save this design and give it a run. So this is the synthesized diagram. Actually here you can see here that it has generated all the digital components required for this hardware. So you can go through each and every components one by one, and you can understand how basically this Verilog code is getting synthesized into the digital components. So now let's walk through the test bench. So this is the test bench for this particular multiplier, and here we have declared a local variable which is n equal to 3. That means we can use this multiplier as a 3-bit multiplier. These are the port declarations, and here we have the duty instantiation, and then we have a clock signal, 10 nanosecond clock signal generated, and here we are basically initializing the variables or the signals, as well as we are driving the signals to the DUT. So we are making the start signal here 1, and we are assigning some values to our multiplicand and multiplier input signals. And now, depending on the positive edge of the O_done, that means once we get a positive edge on our O_done signal, it represents that the completion, the multiplication process has been completed, and the result is available at the O_result output port of our multiplier. So we will check the value of O_result output port once we get a positive edge on O_done signal. So this is a display statement here. We will check the log for this product value here, what it displays, and as well as we will also go through the waveforms. So for simulating it, let's select the Altec Rivera simulation tool, and I will check in the open EPWave after run. We'll save it and we will run the simulation. So first let's see what it has displayed here. So you can see here that it has displayed the product value as 31, which is nothing but 49 in decimal, and done value is 1. So once the done value is 1, that means our result is ready, and when we read that port, it is giving us a value of 31. That means this multiplication is correct. So now let's see through the waveforms. So in the waveform, if you can see here, our start signal is going high here. That means at this point we will basically our multiplier will sample the multiplicand and multiplier values, which are basically nothing but 7 and 7. And now once O_done goes high, that means the multiplication is done completely, and we have the output, the product value at this O_result output port, which is 31. So I hope this Verilog code for this particular architecture of this multiplier as well as its test bench is very much clear to you. If you have any doubts, please write down in the comment section. Also, if you like this video, please hit the like button, and do not forget to subscribe this channel and press the bell icon so that you would get notified as soon as I upload a new video. Thank you very much.